Welcome to Advanced Reverse Engineering. We have homework from last time. The homework is program slicing. So you're going to use Capstone and you're going to slice a little bit of ELF code. And I'm going to give you programs that end with a return, so don't panic too much about this. And we'll assume that RAX is live at the return. Now, if you are careful in how you do this, you could use this to do slicing with other stuff live from other locations, right? We're just making this easy for you. I'm going to give you a checkered code. You will extract the block, which ends with the return, and then you'll slice that block. Because you're slicing a basic block, you won't have to worry about control flows, so you won't need to worry about phi functions, and life will be pretty good. Anyway, we're going to construct the backward slice of the block based on the value of Rx immediately prior to the return. And if you remember how this works, we would come in here and we'd say, I care about RAX right here between the leave and the return. I would then go back one and I would say, does the leave line modify anything that I care about? So I care about RAX. Leave modifies the stack, so it modifies RSP, and it modifies RBP, and nothing else. No, it does not. Therefore, I don't need to keep it. Throw it away. I would then move back another one, and I would say, does this AND modify anything I care about? The AND only modifies EDX. I only care about RAX, so no. The answer is no, it doesn't. So I throw it away. I move back one more to this move line, and I would say, does this move line modify anything I care about? It modifies RAX, so I'll keep this line. Now, RAX is an L value, so I remove it from the set. RSI is an R value, so I put it in the set. Notice what I do. I remove first, and then I add. Right? If I do it that way, I'm good. For example, we'll see that on the next line up. So now my set is just RSI, and I move back one more, and I say, does this modify anything I care about? And it does. It modifies RSI. RSI is an L value. I have to keep this line, and I take RSI out of the set. But RSI is also an R value, so then I put RSI back in the set, and my set is still just RSI. And I proceed that way up. This is what you'll get at the end. I'd like you to print out anything that's left in the care set when you get done. In this case, I reach the top and RDI is still in there, which tells me that if I want to know RAX at the end, I have to know RDI at the beginning. If I ever reach a case where the care set is empty, I'm done. Nothing can ever get back in there. So I just stop immediately. All right, hope that makes sense to you. Here's what my code looks like, churning through that with debugging turned on. And here are some hints. Feel free to read and consider those. Let's talk about tracing. So we've seen this a little bit before. There's a Linux command called strace that we can use to observe all system calls made by a process. That's super helpful. When you're trying to reverse a program, you might want to run it, and you might like to know, what the hell happened when I ran that, right? So you run something, you set the prompt, you run it, and it immediately comes back, and you're like, what happened? Did something happen? Did anything happen? You need to be able to know what's going on. Observing the system calls is a great way to do that. So, and we used this way earlier in the class to compare the effect of running with the C runtime to running without it. And running with the C runtime had a big, giant, long catalog of things that happened. With running without the C runtime, just the stuff that we did. So there's an strace. That's in fact the strace from earlier in the class where we ran with the C runtimes. Hello world. It's going to intercept and print all these system calls, and it tries to decode partially their arguments. So you'll see, let's pick one here. There's M maps. Let's pick something that's not an M map. Here we go, pread. So we see the first one, argument's 3. Then there's this long string of bytes, byte string, and then a 784 and a 64, and it returns 784. So it lets you see what's going on in here. Here's a close with 3. I'm looking for a write. There's a write to standard out, which is 1. That's the string we're writing. And a 13, which is the number of bytes to write. And then actually writes it. And so we end up with the output mingled in here, which is not great. And the return value is 13, because it writes 13 characters. You can split those out. You can pipe the output of this to a different place than the output of the function itself. But there you go. So that gives us some interesting information about what happens when we run this piece of code. Alternatives to strace. It traces system calls, but what about other APIs? You might like to know about library calls, right? I mean, these are system calls. But what if it's only calling stuff in the standard library? What's calling printf, right? Let's go back. Where's printf in that? Oh, printf in there. Oh man, printf is not a system call. Write is a system call. Printf is a library call. Oh man. Is there an ltrace? Yes. Turns out there is in fact an ltrace, which can trace library calls, but also trace system calls. We're going to use ltrace. So I say ltrace of echo hello world. Boom. And I get nothing. That's not ideal. I mean, I could probably do better by having something, anything. Let's try something else. So I try it with the -s, right? So up at the top you can see ltrace -s echo hello world. I get the same thing I got from the other thing, from strace. How's that helpful? I mean, it's prettier, I guess. It puts sys in front of syscalls. That's handy, right? That's handy. But it's the same information. It's not giving me the library calls. What's going on? So I can add a -i, and I can see the instruction pointer. That's something. It's just not helping. All right, so I'm frustrated and annoyed. What can I do about this? Well, in order to understand what's happening, I have to tell you about something else, and that something else is Linux security modules. So LSMs are compiled directly into the kernel, and they control access to kernel objects, right? Files, inodes, tasks, credentials, IPC, system calls, right? System calls interface with the kernel, etc. And these use the LSM framework to implement mandatory access control. We call those MACs, M-A-Cs. So you can read more about it at that PDF, and you can read about how you can hook the kernel in various ways, and that's defined by the LSM interface. So the LSM interface gives you a generic way to implement security modules, and then it's up to you to decide what you want to implement. That could be, different security module implementations, and there are. So, for example, suppose you want to open a file. You'd use the open system call, rex = 2, and you check the file permissions. File permissions are discretionary access controls, or DACs, right? Why are they discretionary? Well, you can set them, right? You can modify the permissions on a file yourself. You basically are telling you, I want this file to have these permissions for me, right? And so, as the owner, you have discretion to set those. It's not mandatory. It's not something that's enforced by the entire system. Okay. So, if I want to open a file, first I check the file permission. Is this file readable? Is it readable by you? Are you the owner and have read permission? Are you in the group and the group has read permission? Does everyone have read permission? I'm going to check that first. If that passes, then I'm going to call all the open hooks for each of the enabled LSMs. I'm going to say, hey, you are the enabled LSMs. Is it cool if this user reads this file? And if any of them generate an error, I'll deny permission. What are the major LSMs? Well, there's SE Linux. It's an attribute-based access control system. We'll talk about the difference in just a moment. SMAC is another one. It's used in the automotive world. And in Tizen, if you're not familiar with Tizen, that's a strain of Linux coming out of China. There's AppArmor, which you may be familiar with. If you use Debian, you probably see messages go by that mention AppArmor. That's a path-based Mac. And you may have heard of Tomoyo, which is an embedded one, and it's another path-based Mac. I wanted to have two of each kind. This is my ARC to save them from the flood. So attribute-based security encodes security constraints into the attributes of files. That's it. Security for a particular file is fixed no matter how you access it. But the file has to exist. If the file doesn't exist, where am I storing the attributes, right? I'm storing the attributes associated with the particular file. So a weakness is, what if there's not a file? Then the rules don't necessarily apply. Path-based security does it a little differently. It encodes the security rules based on paths. So different paths to a file might end up having different security contexts, but you can also specify rules for files that don't exist yet. So suppose I somehow managed to create a file that I normally shouldn't have access to. Well, if I can create it, if it doesn't exist, and I get to create it because it doesn't exist, then I can control the attributes. On the other hand, if it's path-based, then maybe I can't get to the file because when I created it, it matched a path, and now I'm locked out of it. That's frustrating. But maybe I can find a different path that fools the system. Maybe I can find a path with hard links that lets me get to it. Maybe that would work. So there's different pros and cons to these two different ways of doing security. You should just be aware of them. There are some minor LSMs that you can select and load alongside a major LSM. Okay, so in addition to the major LSM, like AppArmor, I can also load a minor one, and one I might have in there is Yama. And you can read about Yama there. Yama controls the scope of ptrace. That's the ptrace system call, which is number 101. Both ltrace and strace are built using ptrace, the ptrace system call. Okay, we talked about this when we talked about GDB. And here are the Yama modes. Classic ptrace permissions. A process can ptrace attach to any other process running under the same UID, that's your user ID, as long as it is dumpable. What does it mean to be dumpable? Dumpable. It didn't transition UIDs. No, I didn't privilege elevate. I didn't start it privileged. And I haven't called PR control to mark myself as not dumpable. Okay? There you go. So I can actually say I don't want to be traced. And no one's changed ptrace me. So that's classic. If I have the file, if I own the process, I haven't elevated, I'm allowed to trace. Then mode 1 is restricted ptrace, and it's in gray because it's the default for now. Or at least for now on the Linux that you're using. A process must have a predefined relationship with the inferior it wants to call ptrace attach on. A predefined relationship? What does that mean? Well, it might be the parent of that process. You're allowed to call ptrace attach on processes that you start. For example, you might be GDB and you start a program and you want to debug it. You're allowed to call ptrace attach on that process because you started it. Make sense? All right. 2 is admin only attach. Only processes with capsys ptrace may use ptrace, either with ptrace attach or through children calling ptrace traceme. So much more restrictive, right? Only if you're able to if you're a privileged user I was able to set these can you actually trace or no attach. No process may use ptrace attach nor via ptrace trace me. And once you've set that, you can't change it. So why would you do that? Well, you might be delivering an embedded system that goes in a controller for critical infrastructure. And as we talked about before, this tracing stuff, that can be a vulnerability. Right? We see how GDB uses it to modify a running process. So in this case, you'd want to lock people out so they can't do ptrace attach. What mode are you in right now? If you want to know, you can go look in the proc file system. Proc sys kernel yama ptrace scope will tell you what it is. You're probably in 1 right now. And we can switch that to the most permissive mode, which says if I own it, I can trace it. And we do that with a syscontrol, sudo syscontrol -w, kernel yama ptrace scope equals 0. Hooray! Let's assume we've done that. Let's go back and let's try to trace something. In this case, we're going to trace the malloc, freeze, calyx, and realix that occur when I run Python and I print hello. And I find out that I malloc some stuff, I freeze some stuff, I realix some stuff, I calyx some stuff, I print hello. So there you go. That's a way to have a look at what's going on in your functions. You can use filters. So you'll see how I use filters up there to just see the specific memory events. There's tons more to this. Read the man page, search online. There's some good examples online of doing this fun, interesting stuff. All right, with all that out of the way, let's talk about type-based decompilation. Decompiling a program requires that we reconstruct a lot of semantic information. And a lot of times the way we do this is by guessing. We say, well, I think it's plausible that this is true. And then we can look for ways to refute that. Right? So I might say, I think they're checking for null in a list of pointers. And that implies that we have a list of pointers. And so we can go and look and say, are these being used like pointers? And if they're not, well, maybe my assumption was wrong. So we're always looking at things that are plausible. Semantic information has been lost. Intent has been lost. We're doing the best we can with imperfect, incomplete information. We can get close to this with something called type reconstruction. Now, during this process, we decide that part of memory or something that's being pointed in a register or something else is a certain type. And we do that by observing how it's being used. So if I see that I'm using RSI, for example, as an address, so it's always appearing in square brackets, it's probably holding an address. If I see that I'm incrementing RAX and maybe adding values to it like 17 or 24. Those are weird. 24 not so much. That's a 25. 25 is not a multiple of 8. Sorry, to pick the bad example. That's weird. That's probably not a pointer. That's probably an integer. So I can, by observing how these things are used, I can begin to get a sense of what they might be. So that is what Alan Mycroft proposed in his paper on type-based decompilation. Program reconstruction by type reconstruction. He says, okay, I've got an unknown program, I know what it does, I'd like to decompile it, and the way I'm going to do that is by trying to reconstruct the types. Alan Mycroft has done a number of things in his career. One of them is he's co-founder of the Raspberry Pi Foundation. I think that's kind of neat. If you have Raspberry Pi, thank Alan Mycroft. We describe a system which decompiles, and he puts reverse engineering in parentheses, so to him reverse engineering here is decompiling, right? Because engineering was apparently not making the program, but compiling it. So reverse engineering is decompiling it. I'll give him that. Decompiles C programs from target machine code by type inference techniques. Okay, that's interesting. I think that is itself an interesting thought. He goes on to talk about a bunch of other things, and we'll cover each of those along the way. He mentions RTL. He mentions SSA. He talks about a number of things. We'll get to those. The paper mentions two acronyms, two languages that you might not be familiar with. He mentions BCPL, and that's a programming language, and that's actually what motivated a lot of this paper's work. And he mentions RTL, the lower level code used in the paper. So let's ask the question, what are these, and do we need to know? We probably don't, but it's worth finding out anyway. So as an aside, I'm going to tell you about BCPL and RTL. So the 1960s were a very quiet decade. Nothing was really going on, nothing much happening, very boring. And so as a result, the people at Cambridge were sitting around, bored out of their mind, and they decided to create a programming language. And of course, since they were at Cambridge, they decided to call it the Combined Programming Language, or CPL. This language had lots of features, thus the combined part will combine everything that anyone's ever done in this one programming language. And that made it hard to compile. You can look at the same approach that was taken for Ada. Ada's hard to compile. So as a result, they said, well, it's hard to compile all of this all at once. Maybe we can compile it down to an intermediate language. Or maybe we can build parts of this in an intermediate language and then implement the rest of it in that language. This was the Bootstrap or Basic CPL, or BCPL. The problem was BCPL was a real language that worked, that had a compiler, that worked really well, it was simple, and it was easy to port. Now that last one is really important because think about the world at that time. People are trying lots of different things, right? There's a myriad of different machines out there in the world today and a lot of different processor architectures. But odds are good that you have a Windows machine or a Mac or maybe a Linux machine. And that Windows machine or Linux machine is probably on AMD 64. That Mac is on ARM. Almost everything is probably ARM. We have a much more limited set of machines to target. Now, back in the 60s, it's very likely that the machine you have, maybe it's got a 36-bit address bus. But the one up the road that you also want to use, it's got a, 19-bit address bus. Weird stuff's happening. So being easy to port is great because we haven't sort of settled down into the sort of monopsony that sort of funny world we have now. So being easy to port was really important. And it was therefore, this language was incredibly influential. So CPL is a dead language, but BCPL lives on as C. Because it eventually evolved on into C. Now, I say CPL is dead. There's actually now a working compiler for it, developed shockingly recently, in case you really wanted to write some Cambridge programming language code. So here is a picture of some language families. There's a ton of these online. They're all a little different because no one can quite agree on exactly what influenced what. Right, so for example, in this one, logo has no descendants, when clearly it should have some descendants. And so you can see BCPL right about here. There's BCPL. I put the little blue thing above it. And there's C. It comes right out of it. BCPL straight down to C, and then to Objective-C and C++ and C# and tons of other things. So I got challenged in the previous class where I was told, hey man, C evolved from B, get your facts straight. And my rebuttal to that was, here is Dennis M. Ritchie writing about how he and his friend developed the C language. And he said, derived from the typeless language BCPL. I declare this to be definitive, right? So Dennis Ritchie agrees with me. I'm happy. So where does B come into the picture? Challenged by McElroy's feat of reproducing TMG. So I don't want to get into TMG. It's the meta. Don't worry about it. Ken Thompson decided that Unix, possibly hadn't even been named yet, needed a system programming language. There's Ken Thompson over on the left-hand side there. After a rapidly scuttled attempt at using Fortran as the system's programming language. Hey, you Unix and Linux users out there, you almost got Fortran as your system's language. Wouldn't that have been great? He instead created his own, which he called B. And B can be thought of as C without types, but more accurately, it's BCPL squeezed down into just 8K of memory and filtered through Thompson's brain. Its name most probably represents a contraction of BCPL, though an alternate theory holds that it derives from Bon, an unrelated language created by Thompson during the Multics days. So there we go. So BCPL is where we get C. And you might wonder, what's in BCPL? What does it look like? It looks like the top right-hand side. So you can see there are header files you can get. It's got brackets. It's got a return value. And the fun thing about that thing up there in the top corner is that is the first ever Hello World program. The first ever Hello World program was written in BCPL. It's the first brace language, first one to use curly braces. It's the, it introduced the / comment form. Why that wasn't carried over to C, I don't know. It was sort of perfect. It introduced the virtual machine bytecode approach. It didn't have types. Everything was a word. And it was platform dependent. So if your word with 36 bits is what you got. It made major use of Hungarian notation. That's where you encode the type of a variable in the variable's name. If you've never done any programming that used it, it's got its proponents and its opponents. I've worked on projects where we used it. For example, you would use P for pointer and SZ for null terminated string. So you'd have like PSZ foo, which would be a pointer to a null terminated string, and the variable name was foo. You'd use that as a variable name. Some compilers could fit into 16K, which is great. It eventually spread to support 25 different architectures before it finally gave way to C. And it was the first language used on the Xerox Alto. If you don't know what the Xerox Alto is, you don't know any computing history. You should go read up on the Xerox Alto. It was the first computer designed for a GUI, and that's the one that Steve Jobs went and saw and was inspired to create the Mac. It was stripped down to create B, and then types were added to create C, and then objects were created to make C++, and then chaos was added to create Java, and then it was simplified to Go, etc. It is just barely older than I am. The first compiler for it was written in 1967. And bracket languages are everywhere now. There's a ton of them. BCPL is the first. Syntax originated with BCPL and was popularized in C, and there's a lot of bracket languages. So, what is RTL? RTL is Register Transfer Language. It originates in this paper, the design and application of a retargetable peephole optimizer. I'm not going to explain what a peephole optimizer is. You can look it up. It's a clever little technique where I sort of set a window and I walk through the code looking at that window on that set of instructions. You can have a field day with that. But what it is it's an intermediate language. It lifts the processor semantics to a more abstract level. So this is great. This gives me a really nice way to compile stuff. instead of me having to compile C to ARM and C to AMD64 and C to AVR and C to PIC and C to 68K, and then do the same thing for C++ and Rust and Fortran and all these other languages, what I can do instead is I can compile C to RTL, and I'm done. Somebody else will then build a compiler that compiles RTL to ARM and AMD64 and AVR and PIC and whatever. So that's great. I get a language infrastructure for the back end that outputs bytecode, and I get a language infrastructure for the front end that compiles my source language to RTL. RTL is the lingua franca that lets them communicate. And there's many different ones, right? There's GCC's RTL, LLVM has target independent code, Ghidra has its P code that it uses for analysis. Those are all intermediate representations, IRs, and they are all RTLs, register transfer languages. So BCPL doesn't have any types. So what if you wanted to port something from BCPL to C? And C does have types. In that case, it's going to help you if you can infer the types that were present in the original BCPL. So Mycroft needed a generic way to represent operations. Not quite assembly, that'd be too specific, but lower level than source, with elements that were common across all platforms, and that was RTL. Thus his use of RTL and the motivation coming from BCPL, which is being replaced with C, and there was a big, huge body of programs written in BCPL. So back to Mycroft, now that we've got the motivation piece out of the way. A correct optimizing compiler is going to transform many different valid source programs to the same binary code. We've actually seen that. If you compile a hello world with printf and a /n at the end, and you compile a hello world with puts and no /n at the end, you get the same output, right? Because there you go. It's going to compile many input source programs to the same output program. It's many to one. So it's not a bijection, which means that a compiler is not an invertible function. Okay, make sense? Many things get mapped to the same thing. When you have a function like that, you can't invert it and get a function. You can invert it and get a relation, but not a function. So I can look at the output assembly, and I don't necessarily know what the input C source was. I don't know, right? Unless someone left it lying around, I'm not sure. It could be any of a number of things. And so decompilation is concerned with giving me back a semantically equivalent source code program. That's hard. That's really hard. Okay? Very difficult. Now, in the ideal case, in a beautiful, perfect world, I could take my original source, P, compile it to a binary program, Q. I could then extract from that a decompilation, which we'll call P prime, and I would find out that was equivalent to the original program P. And that would be great. But it turns out that's not just hard, it's one of those things that's essentially undecidable. So there we go. So Mycroft presents an intuitive example of doing his type-based decompilation. And so his intuitive example are those little 4 instructions that are over on the left-hand side. Now, that's written in Mycroft's register transfer language. And so we need to think about that a little bit. So R represents a register. So R0, R1, R2, so on, are the registers. Load W loads a word. And the order of operands is the opposite of what we've been looking at so far. It's source destination. So let's pick on one of those lines, and let's start from the bottom. Return is just return. And the return value goes in R0. Exclusive OR of R0 and R1 The first two are the arguments. The last one is the result. So I would take R0, I'd exclusive OR it with R1, and I would store the result back in R0. For multiply, here I'm multiplying R0 by itself and storing the result in R0. So this is squaring R0. And then for this load word, a little bit tricky here. You see the square bracket, so you should be thinking address, and that's correct. I'm taking R0 as an address. I'm adding 4 to it, and then I am taking the contents of that and storing it in R0. So again, I'm going to the address pointed to by R0 plus 4, reading the 4-byte thing out of there, because he's working in a 4-byte world, and I'm storing that in R0. So I'm loading from memory. Alright. For his intuitive example, he says, let's just decompile it. Ret returns R0, so we'll just write return R0. There are 2 arguments to it, so we'll just say R0 and R1. Right? The arguments will be R0, R1, R2, etc. in that order. For the first thing, I'm going to R0 plus 4, so I'm going to cast that value to an integer pointer, and then I'm going to dereference it to get the contents, and that's going to go in R0. Then I'm square it, then I exclusive OR it with R1 and put it in R0 and I return it. There we go. Very basic calling convention here is that the arguments go in R0, R1, R2. Return value goes in R0. Now, we can consider live ranges for each variable and give a new name to each one, because we want to convert the program to something called static or single static assignment or static single assignment. There's no uniform agreement on the order, I don't think, and that's a convenient form for further analysis. So let's take a look at this guy right here. So in this, we're treating R0 as an integer pointer. And you'll see that's happening right here. So I take R0 and add 4. Now I can't cast R0 to be an int pointer first. If I did and I added 4, I'd actually be adding 16 because of pointer arithmetic. So what I do is I add 4 to the raw value, then I cast it to an integer pointer, and then I can dereference it. Aha, right? So that would really, if ints are 4, that could become this. Now I cast R0 to an int pointer and I add 1, which moves ahead 4. And so then I could maybe rewrite it like this, if it's just an integer pointer already. Or I could rewrite it like this, as an array reference. And in fact, that's one thing we can do. We can improve this by saying, you know what, I think this is an array reference, and so I'm going to improve that by making it an explicit array reference and declaring R0 up here not to be an int, but to be a pointer to an int. There we go. That's better. So that's the kind of thing we want to do. We want to figure out these types and replace them. Now, he does mention, so we have named each value. We can substitute, paying attention to side effects, and sequence points. He mentions sequence points. What's a sequence point? A sequence point is a place in program flow where a computation is or should be stable. And what that means is all side effects of prior computations have completed. No side effects of subsequent computations have occurred. It's this idealized state, and you'll find it in the C standard and the C++ standard and other language standards as well. It's a place where we want everything to be well defined. And those occur in C. They are usually where you have a comma or a semicolon. Now, in reality, the processor is always doing things in parallel as much as it can. So side effects for a prior computation may still be going on, and side effects for subsequent ones may be happening at the processor level all the time. But in terms of what the language interpretation, we want the language to function as if this is true. All right. So we decompile the program into plausible source. We keep in the array reference. You see we have it again here. We square it. We exclusive OR it with R1. We return that value. And so there we go. We've decompiled our initial stuff into plausible source code. Is that what it originally started out as? I don't know. We don't know. All right. So what Mycroft does next is he says, here are the expressions in my little register transfer language. And he only gives you a few, right? Because he's writing a paper. He didn't need a million. So you have moves, loading a word, exclusive OR, add, storing a word, move of a number, a literal number into a register, and a move of a 0 into a register. And for each one of these, he gives you a generated constraint. He says, you know, if you see this line, putting 42 in R7 or some other literal value that's not 0 into a register, we can conclude that the type represented by that register is an integer. But if it's a 0, it could be an integer or it could be a pointer to something, because null is the same as 0. So that's the kind of thing he's capturing in these constraints. Some of them are more complicated than others. For example, here's one. We say T0, the type of R0, could be an array of things of type T3, or the type of R3. Got that? So this is an address pointing to something. It's pointing to an array. What's there? Stuff of type R3. Because that's what I'm storing this in. I know that. I might also conclude T5 is an int. Type of 5 is an int. The type of 0 is an int, right? Because either one of these could be added to a pointer, and the other one could be the pointer. So maybe R5 is the pointer, and this is the offset. Maybe this is the pointer, and that's the offset. And so we have two cases over here: pointer offset, offset pointer. So I explained that badly. When he has a number in front of the brackets, that could be the pointer and that the offset, or that could be the offset and that the pointer. That's basically what he's trying to capture here. And this works in C. You can give it a try. You can write your C program and you can, move the array reference into the square brackets or out of the square brackets and put the index in there, and it works the same either way. It just uses the pointer arithmetic to do the math. That's all we have time to cover today. We'll go in more depth with it next time, and talk to you then.